So Gregor first. Gregor inserts directly from the lab, and he's gonna talk to us. We go back to the topic of over the air update, but now we don't only worry about if it's secure, if it's safe. So
Thank you very much for the short introduction. In the very beginning, maybe I need to excuse myself because we had very technical presentations directly before, and I will by far be not so technical. So I'm more a formal guy, and maybe I'm a little bit abstract for you in some parts. But I have three main messages to you, and they are quite simple. The first one, DLR is more than only rocket science. The second one is we are also doing SDV and especially safe over the air software updates. And based on that, we're looking forward to integrate with Eclipse open source projects and especially with the ESCO project. So if you're feeling uncomfortable with my talk afterwards, it's fine to fall asleep with having these three messages compiled. Otherwise, with the remaining part of the talk, I will explain a little bit. You will get some technical details about why I'm telling this and where we might collaborate in the end. So I will motivate a little bit about that. So DLR is more than avionics and rocket science. Of course, the main part is avionics and rocket science, but there's also sustainable energy and fuels. So there's also part and really a big part about transportation. And where we're doing maritime domain, so automated vessels, autonomous drones, also maritime simulations, so bridge simulations, ship and vessel handling simulations, and human-machine interfaces. We are also doing trains and railways. So here it's a lot about aerodynamics, about new railway train concepts, and we're doing automotive. So here we have modular vehicle concepts and also fuel cell cars, future cars, but also dynamic simulations and so on. So lots of transportation topics. And as one part of that, we are also dealing with autonomous driving and SDV. And here we have, as my topic is a little bit formal specifications. I have also a colleague on this today with us. So from this perspective of describing and generating scenarios, verifying scenarios if the car drives correctly, if scenarios are fulfilled or not fulfilled, how they can be simulated, and also on future software architectures when it goes about partitioning software onto mixed reality software onto high performance single key shooters in a complex automotive hardware software stack. So saying about this, we don't believe in the shoot to the moon approach, right? So we don't think that autonomous driving will be invented by one. So there will be one hardware software stack which will come and run at level 5. Maybe this will be implemented stepwise and incrementally. For that reasons, we need safe and secure automated deployment and integration of software parts. These steps will all require fast integration to release and reduced test efforts. And so we need automation and modularization here. And as we have heard also in some talks before, we need transparency. So transparency in the means of observability on the one hand side on the model level, on the other hand side also on the source code level, which means as we also have heard before, shift to the left, stretch to the right. What motivates us, of course, as you can see, what shoots to the moon is the lines of code in the vehicles, right? So which grow up exponentially, and we don't can handle the effort for the integration and the verification anymore. In parallel to this, the number of function increases, or the number of services. In between, there are several paradigm shifts, which again and again reduce somehow the efforts and the challenges we have. Nevertheless, the number of services is increasing. And with that, the number of personalization also is increasing. So functions are more and more changing. Everyone gets an individual car, everyone gets individual function, individual services. And they even depend on the position where you're driving. So that way you need to change and adopt the car. Often we expect there will be 15 to 200 software updates per year. It might be selective, it might be supportive, and adaptive, different ways of updates, but it will be a huge number, and the preference are too many is better. For that reason, we had a project which was up to date some years ago, and we developed holistic over-the-air software update paradigm from the conceptual side on the one hand side, but we also implemented the prototypes, which is mainly or was mainly based on formalisms and processes, but also on guidelines somehow for these software updates, how to do them, for the updatable hardware software platforms, how to integrate the process into the dev phase, into the ops phase, and of course, how to step through the deployment and how to roll it out for the self-lead system of systems. And it's mainly based on 3 phases, as I've already mentioned. We have the dev phase. We have the dev phase, where we have development of new functions, the characterization of that. We have when it will be provided to the repositories, design time check, such that only valid updates are available in the cloud. We have the release of the update. Afterwards, we have the situation where we come to the deployment when the car will receive the download, the update. And it will be updated. The compatibility and mediation of the software needs to be checked again, because we need to ensure that there's no difference between what is available or what is the decision about the integration in the cloud and the situation we have in the car. If it is fine, we have the download and the installation. We have a further verification and activation step in the car itself. From that point, the online monitoring in the car started. Then we are in the monitoring phase, and data received from the online monitoring might be transported back to the developer, back to the cloud, to allow for offline monitoring and to again start with a new update for the reason of bug fixing, for the reason of improving the performance, or for the reason of having new functions again. So this was the main concept and was the main paradigm or approach. And behind that, as quite often there stands a model-based development approach, which is described by virtual modules. These modules, in our case, are talking mainly about resource properties, so execution times of a certain CPU, memory pages, and memory usage, about I/O usage, and things like that. And it tries to be compositional by the idea of providing and consuming interfaces, and internal definition of resource usage for every function that is meant to be part of this module. So there's a description which functions are part of a module, is characterized in terms of what resources it requires. Can be checked whether these resources are provided by a certain hardware, by a certain hardware module, by a certain hardware composition, and so on. And these properties are expressible by are expressible in a formal language, and they can be checked. So in this way, we can connect hierarchical these virtual modules and have, on the one hand side, as I mentioned before, virtual integration testing in the cloud, so based on models, based on formal properties, based on simulations. But we can also deploy or generate and deploy monitors for that to ensure the same properties also at runtime. And This is, as I mentioned, I will not go into details, but this is how these properties can be expressed in formal languages. On the very top, we have the timing properties expressed in terms of contracts. So this is how people who know about contract-based design. This is assume guarantee reasoning. We have assumptions that, for example, for camera processing or image processing software, images occur every 5 milliseconds, and a reaction on that by computing, processing these frames happens within 3 milliseconds. So there's a simple timing property. And below we have assumptions regarding the configuration of the operating system, the hypervisor, and available CPU cores. And the component itself again guarantees what a CPU core it will allocate or will use when it is available. And this way you can check if the available resources are sufficient to execute the software, and whether the integration of several software components are able to share resources on a given environment. And as I mentioned before, this was implemented for a simple update with system architecture, which at that time was an NVIDIA Jetson HX Xavier, running in the real-time Linux. And we had several partitions here for the system. And some of them were dedicated to the update middleware, so the update subsystem, running update manager for different parts. Also external assistant components that are updated through this gateway. That's why we have multiple partitions for the update management. We have, of course, the user subsystems where we have critical or safety critical and non-critical software applications. And in between, we have a monitoring subsystem where the decision about the properties is executed in runtime. So, of course, these decisions can take some effort. That's why we, in this case, put it to a dedicated partition. And over the whole system, of course, observers are distributed to get all the data based on timed events or research information. And through the update manager, of course, the cloud is connected. So when it's outside system update manager and the update master here is a repository where the data is available and so on. And the whole communication system, this is more or less what the engine looks like. Using a short video. Unfortunately, I don't have a demonstrator with me today, but using a short video, I will show you how this looks like. This was a demonstrator was developed in the TASTE project, and it just shows briefly the update process. It shows a car that is following a track. And we will update the lane detection function while the vehicle is driving. And the first version currently recognizes only the outer line of the track. The update will later recognize both lines of the track. And in the back, you see a screen which explains what happens here. And at the top, it shows a cloud where there are software versions are available. And below there will follow the screens or the visualization of the internal data. Use pause it for a moment. Oh, sorry. Explain. This is the computation chain or the chain we see here. As mentioned before, we have updated monitoring middleware partitions and the user partition, I would say, and critical one and a non-critical one running on top of a hypervisor. In this case, we already use the Renesas Arca hardware. There's a hypervisor channel. And what we will now see is that up here we have the lane detection software, And this will be exchanged. So we will receive the new version of the software below here. And this explanation about the monitoring middleware that is generated from the contracts. So here we now see the recognized track with a detection of the right lane here. And then the cloud, which is showing up here, and you see here a new version of the software being available. Car is driving with the color simulation. Before the update is released, the resource contracts are checked. Happens here, and which is also shown at the screen. Timing properties need to be checked. This is now fine so far. Okay. New driving functions can be downloaded. And you see the function is unnated to the car. There's the old version is running, so both are running in parallel. Sometimes a runtime validation. Now both are running in parallel. And the checks are fine. The switch takes part or happens. The new software is activated. You can also see here both lanes are now detected by the new version of the software. The old software can be unloaded. And monitoring starts, can be used for the offline processing afterwards. So this is a very small demonstrator we used here, and we will also use for other automotive test setups, which fits quite well to what Islama said before. So then more or less a blueprint, simple example showing this quite fast and a low level. That helps us to understand and easily check forward what we did here. And now in July, we start towards a new project UP2DATE4SDV, where we want to go on with this approach in general. And you already see, okay, yes, four main goals, I would say. So we want to have a responsible connected zone vehicle hardware platform, which we want to abstract by a hardware abstraction layer here. So we will also cooperate with SDVs. And target resource composable software deployment, execution, reference layers, and at least at the operating system level, in the best case, including the middleware abstraction. We need the connection car to cloud to car, together with the orchestration and reconfiguration plane. We also heard a lot about that today in the morning. And we need to connect or want to connect to the cloud-centric CI/CD and DevOps framework. So being available to detect execution of the updates in virtual ECUs. So this covers the complete update cycle. And as already mentioned before, a central concept or main concept for that is, of course, the modularization and monitoring, and control of the whole stack. So on a model-based level. And this brings me to the outlook and the opening to lots of contributions and interactions. Because as you can imagine, there is lots of connections to Eclipse SDV projects we saw today. So in the whole range of deployment, development on the one hand side, but also deep down into the operating system and the hypervisor topics. That's why I used the S-Core here. It highlighted a little bit where we might see contributions, which where we will have also potent solutions where we want to integrate or we can contribute to the Eclipse project. Also dependencies, which to my feeling were a little bit less mentioned in the talks today, because we, of course, want to have a fast solution for the S-Core stack, Yeah, in best case until the end of the year was mentioned, right? Version 1.0. But no, it's v0.5, sorry. But nevertheless, we need the model-based definition for these blocks of these dependencies. And here we strongly offer to communicate and to interact. And we have to look forward if we afterwards can have a exchange on that. And currently, without these interactions, we're currently going forward with the setup. So we're working on the Renesas archive together with Shanisi setup eyes on Xen and Zephyr. We have connections to ELISA and works with System D and Sapient by Haploids. So this is where we are currently active. And if you see collaboration potential here, I would look forward to talk to you. And this brings me to my conclusion. So software integration is a major bottleneck, and modularity and observability is what we consider as key properties for the model and for the code level. So would be happy if you consider this. And UP2DATE, we developed an integrated formal model-based concept for safe and secure over-the-air updates based on contract-based design, virtual integration testing, and runtime monitoring. And we want to extend this to a modular software-defined CCAM vehicle that is updatable, reconfigurable, and virtually testable from the cloud. So we're doing more than rocket science. We have a social responsibility at DLR, and that's why we value open source. That's why we look or we try to contribute to work of German and European industries. So here we offer also operations. With that, we tend towards fair, green, and efficient transportation technologies. So for those 3 points, we consider SDV and safe and secure over-the-air software updates to be a key factor to achieve that. And to my point, I explained it a little bit. That is a little bit neglected in lots of these architectures. We would if we can contribute here. We're looking forward to the discussions. Thank you very much.
So, questions.
Thanks for the presentation, very enlightened, and thanks for sharing that with us. You mentioned already some SDV projects. What you didn't mention is, for example, the project Canto, the Vehicle Update Manager. Did you see it already?
Yes. Indeed, maybe this could have been another slide we haven't the time for, but we are very new in Eclipse SDV, and we are not yet very good oriented here. So maybe this is also a call. Please help us if we don't have you on the screen. I already mentioned to my colleagues, please have a look at Canto, but it was not yet clear. I think we already started a little bit to look at Kairos. We looked, of course, at SCore. UPROTOCOL is a topic. We have the connection, as I mentioned, to ELISA, but there's also ThreadX, right? With a big stack, we don't have everything on the screen currently, but we are open for contributing to the exchange, and maybe we can together arrange some things that we find the proper things where we can cooperate and where it doesn't ship maybe. Maybe all the suggestions are wrong currently at some points, right? So
this is perfect. That'd be great. Thanks.
Thank you.
Yeah, so that's
So I will come with a provocative question.
Oh my God.
With many OTA software update solutions out there, why should I take yours?
N+1, right? No. Why should you take ours? We considered, so on one side, we already worked together with TÜV. So they had already a look on that and said, okay, the ideas are quite good. Of course, it's not automotive grade up to now. So there are many parts which are not automotive grade up to now. So lots of work still to be done. Nevertheless, we have covered more or less, I would say, the whole, at least to our perspective, the whole range from the model down into the code level. And to my feeling or to my best knowledge, this is missing at many points. We have many projects which focus only on the code level because there are already enough problems, right? So don't misunderstand me, but take me wrong. But we have the connections also from the model perspective. We have to admit we are looking mainly on the resource and on the timing properties. We are at our side currently completely not looking at the functional level, right? We don't verify whether the time right correctly. That was my colleague that asked, but so the approach is mainly does upload fit into the resource constraints of the system regarding the timing requirements and the resource requirements. And here we have the connections between models down to the code.
Yeah, that is what I wanted to follow up on. It looked like you are focusing on updating the software while it is in use. Is that correct?
We already also had a look at that, indeed. So,
and what you showed in the video?
Yeah. We are seeing in the demonstrator, there was two software versions of the two versions of the software running in parallel. And so this is kind of shadow mode execution where you check whether they are both running properly and have the same outputs or have regarding certain consistency checks and certain properties, the agreement, so kind of voting things out. Do they agree with each other?
Is that a relevant property of the whole process? I was wondering because the over-the-air update mechanisms that I've seen so far in automotive is mostly we download the software, and when the car is parked, the next time we do the update, switch the partition, start up, that's it.
Completely agree. And this was also something we came to the conclusion, is that really relevant to have it at runtime? Probably not. But we had want to have at least the downtime as short as possible, right? And that's why we want to have it modular. That's why we don't want to reload the whole partition, but only parts of that. And here this dynamic might be relevant because we might not need or might not want to shut down the whole partition. Maybe we only want to shut down the function or the container or something like that. This is maybe a synchronous between what is it mode?
That's definitely true. I mean, in automotive, normally you're making the switches. I really like the idea of switching only a certain application. It has definitely a lot of benefits. You have to also transfer less over the network. But have you thought about dependencies also for the
just wanted could be a direct follow-up on myself, because the question of dependencies is whether it scales, right? For some part it might, for some part not.
Well, maybe containerized applications can.
Yeah.
Maybe we can have a chat.
Exactly.
What is
Okay.
what is
I do have a question. So in one of the first slides, you show update of the software, but also of the hardware. Did I see it correctly?
I mentioned it
Can
indeed.
you give some more context?
We not yet did that, but we are currently working on that. And exactly this is it. Don't give me a second. Let's be back on the screen.
what is going on?
Not today for SDV. We want to have a modular hardware setup. So to let's say emulate the initial high performance central ECU, and it will have multiple compute modules. And we want to change them. So indeed, we want to change them, not at runtime. Probably this might be an issue. Yeah, but we want to see whether we can apply the more or less same approach also for the hardware. So having the same software stack running, but changing the hardware to a more performant hardware, for example. Right? And there are simple cluster computers where you can change these compute modules, and we can check if we can apply it also for that. this is one goal of the UP2DATE4SDV project, because indeed many people are thinking about performative software updates, and this will be the more frequent part for sure. Nevertheless, to extend the life cycle of the car, extending the compute capabilities of the car might also be a use case. So swapping a compute model to a more performant one might be relevant in the future.
Interesting concept. I mean, I've never heard of this project before, so that's I mean, good that you
You had, but you didn't know the name before.
I didn't
It
know.
was changed by the European Commission.
Okay.
Yeah,
We have a question from the online audience asking about if there's anything specific about the Renesas hardware.
Reason was that we already could work with a quite heterogeneous hardware. It was not the most powerful one, which indeed was also an issue for us because AI functions are not so easy to run there. But there will be a new Renesas platform which will be quite performant. It's performative. And yeah, but this was the main reason to use the Renesas Arca and not the Aurix. Yeah, but we are open to see also what other hardware will be there. We are already looking also at Orange, but here the problem is that this is not a clear stack. We by far comes through all these monitoring things. We want to do that way. So it's difficult. And regarding the Aurix, currently my feeling, please tell me if I'm wrong, even less powerful here. So from my perspective, Aurix would be an end device, not a central ECU somehow, and targeting a central ECU is currently.
Thanks a lot.
Okay.
I hope we'll hear more from you in the future.
Thanks for me. Thank you.